Hello everyone. Welcome back to ComSci Connection. This is part 2 of a 3-part series revolving around graphs. Welcome back. It's been a long time. It's been about 10 minutes for me, but let's jump right back where we left off. So this is the graph image that this image represents the graph that I have built in my code here using the graph class that I introduced in the last video. So if you aren't familiar, if you didn't see the video, or if you need a little clarification on that, then feel free to go back and check out that video and make sure that you are up to speed on what we are talking about. Because essentially, if you aren't familiar with graphs, you probably aren't going to follow this video too well. But we have a graph here with some vertices, or a vertex class and an edge class, and we're going to use that to, or I did use that to construct a whole bunch of vertices and a whole bunch of edges that connect them, and it looks like this. So we are basically going to talk about depth first search in this video. So what is a depth first search? Well, depth first is usually a recursive algorithm. Now, can you do it without recursion? Of course, you could use a stack, but we're not going to do that in this video. We're essentially going to do it recursively, and we're going to talk about why it's going to be pretty obvious as we go through why it's called depth first search, but essentially we are going to figure out one option about traversing every single node within the graph, visiting them and doing something with them. Now, that kind of visit step in this video will simply be just to print the character to the screen, but there is a lot of obvious uses for that visit method and how you could actually attempt to get some kind of usefulness out of your graph that you built and you traverse. So first, before we get into talking about traversing through the example of what a depth first search will actually do, we will look at the actual code and kind of get an idea for how this works. So first, you'll notice I have a public, I actually meant for this to be private, so I'm going to change that. You'll notice there's a public void depth first, which is my basic depth first search method. The only thing it does is take in a starting vertex at which I want to begin the traversal, and then I have basically called the recursive depth first method that I've defined directly below it right here. So you'll also notice that there's another argument on this method, and it is being instantiated as a set of vertexes of type T, and we're calling it visited. So what this means is the set is just simply using the set interface. I believe it's an interface. It might be an abstract class. Don't quote me on that. Vertex is the vertex object I've defined within this class, and then T is going to be our strictly type-bounded generic type for whatever it is at runtime. For this video, it will of course be character. So that will keep track of the nodes in which I have visited. Now, why would I need to do that? After all, this is a directed graph, right? I mean, can't I just simply reach the end of one point and then kind of go back from there? Well, yes, and what I mean by go back, I mean is fall back recursively. I don't mean move back in terms of traversal, because that's impossible in a directed graph. Unless there were additional nodes or edges, excuse me, connecting these two nodes. But and while that is true for this graph, it's still, well, A, it's still a good idea if you had an undirected graph to keep track of the nodes you visited, and B, if I visit F, say right here, from the path of H to F, or the edge from H to F, then you probably don't want to visit it again from D to F. And that's true, you definitely don't want to, just take my word on that. But if you were to, say, have an undirected graph, you'll notice that there is a circle that forms here. Now, in this video and for this graph, this example, this doesn't apply, but if there was an undirected relationship, or if additionally there were nodes from F back to H, back to C, back to B, then I could definitely find myself in an infinite loop that will cause my program to never terminate and quite possibly never reach these other nodes here on the end. So bad ideas all around. That's why you definitely have to keep track of the nodes you have visited So when I call my recursive depth first search method, I send it the same node. Here it's called start, it's my beginning point, and it will be instantiated as a type current in the recursive calls as we iterate through or recurse through the traversal. And then the hash set will just keep track of what I have visited and what I haven't. And my choice to use a hash set was simply for efficiency, so we weren't going to focus on that too much. Basically in the recursive code here, I'm starting out by storing a list of edges, which is the current node's list of edges. So I'm simply just asking it to return the list of edges that node stores, and I'm going to store it here as a list of edges. So pretty simple. Then essentially this is my visit method. Is just simply to print out the data of the current node to the console. I could choose to do whatever I wanted. Very often you would have some kind of method here actually called visit, and you might, well, you'd obviously send it to the node. But I haven't done that for the purpose of this video because it's really not the important part of traversing. I just want to show that we are going to indeed visit the node by printing out the data, and then we're going to add it to our list of visited nodes. So in this video with this traversal type, you will notice that I have added it to the list of visited nodes right after I visit it. I realize how obvious that sounds now that I'm saying it. It's like, oh duh, you just visited it, so of course you would add it to your list of visited. But it's not going to be the same in other algorithms. So that is important to make that distinction. For the recursive depth first, I have added it to my list of like checked off nodes as soon as I have indeed checked it off or indeed visited it. So just accept that for now as a true statement, and we're going to move on. And then what I've done here is for every edge, this is a for each loop. It basically only requires that whatever I am iterating over implements the iterable interface, and it essentially what it does is will go through each edge in my list of edges called edges right here, and it will one at a time store them as an object type edge type T called edge. So again, it's going to go through the entire list of edges, and one at a time it will store each item as an edge, or as known as edge of this type edge. So that's a mouthful, but hopefully that makes sense. It's a for each loop. You can do this with really anything. It's a really basic type loop. And then we're essentially going to get the to vertex from that specific edge. So we know that the from vertex will be the current vertex, or current, as we are visiting that node currently. We're going to get the vertex that the edge points to, or where it connects to. We're going to store that as a vertex type, which is called next. And then we're going to first check to make sure that we haven't already visited it. So we're going to say, hey, list of visited edges, do you contain this vertex called next, which is currently this one. So if it does not contain that, then we are going to recursively call the method again to iterate into further down the path. So we're going to send it next, and we're going to send it the same list of visited edges, so we can make sure that we do not visit same edges twice. So how will this actually work in terms of our traversal? So if I'm starting with A, which I am, then we're going to obviously have only one edge in our list of edges, which is this edge right here that connects A to B. So the first thing we're going to do is get that list of edges, right? Then we're going to go ahead and print the data, which in this case would be A, print that to the console. Then we would add that to our list of visited edges, and then for every edge in edges, we're going to get the edge that we connect to and recursively traverse that. So since there is only one edge in edges, we're going to start with that one. Now we've traversed from edge A to edge B, and we have this time a list of 3 edges. So this time when we go through the list of edges, we're going to one at a time recursively call. But this is where the term depth first comes from, because as you know, with any recursive call, the code is just like any function in that it has to wait at that line of the function call, and it sits there and waits until the function has returned either some value or just simply returned if it's a void method and said, continue now. I finished my work. As with any function call, that must occur. So when our initial recursive call, or our very first call to recursive depth first that was sent to the node containing A, calls this method on B, it's going to sit here and wait. So it's the same is true for B. Even though it has 3 edges, it's connecting it to 3 different vertices, we are going to have to visit one first and wait, and this element of the stack in our program will sit there and wait on node B traversing C until that returns. And as we know with recursion, we're going to continue falling down that trail over and over again. We will not have the ability to visit more nodes in B's list of edges until we have completely fallen back to that level of the stack that's visiting all of B's edges. So that was another big mouthful, but I think we should step through our traversal and see how that's going to work. So as I am in this step of the code and visiting each edge in B's edges, I'm going to get the next edge one at a time and recursively call it. So what that means is we're going to visit one of those 3 nodes. Now, for the purposes of this video, I have added them in such an order that we'll always be going left to right, just to make it easy. So from B, we're going to visit C, but here's where the trick comes in. Are we going to visit D next or H next? And because we are doing recursive, we know that, as I said, we cannot visit any more nodes in B until we've fallen completely back on the stack back to B. And instead, since we are in C and C has at least one edge that we can traverse, we know we're going to continue falling down the recursive trail. And I will go through this in debug mode in just a moment, but essentially this is what's going to happen. So from C we go to H, from H we will go to F, and since F has an edge connecting to I, we will also go to I. Now at this point, because I has no edges, we're going to fall back to F. F has no additional edges besides the one we've already visited, so we're going to go back to H. H is also out of edges, back to C. C is out of edges, back to B, and then B is done with C. But we're back to this step of B, so we have another edge at least in edges that we can visit. And we have 2 more in fact, so we will go to the next one, D. Now here's an interesting step in our algorithm. D has 2 edges, one connecting to F and one connecting to G. And as I said, I added them in the order so that the left most item in this picture would be the first one to be traversed. But what's going to happen at this stage where we say, okay, for each edge in edges, we're going to start with this edge here. Do we get the 2 vertex, which is going to be F, stored as next, and hey, do I contain next? Well, this is the first time in this algorithm, in this demonstration, where this will actually return yes, true. So this BAM or a not or an inverse or whatever you want to call it, exclamation point, will inverse that value and make this false, and we will not call a recursive call. So in fact, our attempt to visit F will be blocked, and we will not visit F. But D does have another node another edge in its list of edges, so we will next visit G, and then G has one node or one edge in its list of edges, so it will visit J. And then again, J has no connections, it has no edges from J, so we're going to fall back to G, G will fall back to D, and D will fall back to B. And B is back to this stage for each edge in edges. Well, we have one left, so we're going to traverse to E. E has one edge, we'll traverse to K. Excuse my lack of purple on that slide. And then K will attempt to visit J, but once again we've already visited J, so we will stop essentially there. And at that point, K will fall back to E, E will fall back to B, B is now out of edges to traverse, so it will fall back to A, and then A will basically reach this point and it will return back to our depth first call here, and then at which point we will return back to main. So let's go ahead and step into debug mode and watch this happen. So hopefully, trying to make this text bigger in the debug section is always hard because it starts to cut off the lower edges of the text, but I have made this large enough for you to see here. So we're going to take a look at, we've essentially jumped right into the first recursive call, and we're going to see that current has data A. So the current node we were on has data A, and also edges here is size 1. So we can see that we have one edge to visit. So we are going to get that list. We're going to go ahead and print out the data. You'll see A has been printed to the console, and then we're going to say, hey, visited, go ahead and add that node so we don't touch it again. Now for each edge in edges, well, we have one, so we're going to step into that. We're going to store that vertex that we are heading to as next, and if I scroll down here, you will see that next has data B, so we can see that we are correctly traversing to B. And then since our visited list doesn't contain B, we are going to call recursive depth first. So I'm going to go ahead and step into that. So we are at this point. Now in B, we're going to get the list of edges. We're going to print out B to the console. We're going to add it to our list of visited edges. And you notice I'm going to start stepping through this a little faster because I think you should be getting the hang of it as we go. Now for each edge and edge, we're going to store the next vertex that we're heading to. We're going to make sure we don't contain it. Just for your purposes, I will show you that next has the value of C, so we know which node we're about to visit. We haven't already visited C, so we're going to go ahead and step into that. Now our current node here is the one containing data C. So we have, at this point, stepped up to here, and our current is on C right now. So we're going to get the list of edges, we're going to print out C to the console, we're going to add it to our list, we're going to go through each edge, we're going to store the next edge. We haven't visited it yet, so we'll recursively iterate, and now current is data H. We are at this point. We're going to keep going, we're going to step down, we visited H, we added it to our list. We're going to go through each edge, store the next vertex, check to see if we haven't already visited it, which we haven't, recursively iterate, or recursively call. So we're now at F. And you can see this is going exactly like we thought it would. Get the list of edges, print out the data for each edge, store the next edge, make sure we haven't visited it, go ahead and recursively call. Now we're all the way down to I. We're at this point. Now we're going to start to see this happen. So you'll notice here on the left, and I realize it's probably a bit small for the video, but you will notice that on the stack trace, I have a whole list of recursive calls to recursive depth first search. And you'll notice that everything below the current one is sitting at line 61. If I select each one of them, you'll see that my top one here is the one that has current data I, so my current node or vertex is the one storing data I, or the bottom one here. If I click on the stack element below that, that's waiting at 61, you'll see that, if you can tell, it's highlighted on line 61 right here, waiting for this recursive depth first search function call to finish and return back to that point. And this, in this world, or this dimension, if you want to look at it that way, the current node is data F. If I go down the stack trace, it's data H, data C, and then data B. So each one of these is still sitting there waiting for their recursive call to return before they can continue. And since I has not been visited yet, let's go ahead and step through that. Now here, where it says for each edge in edges, we're going to notice that edges is an empty list. There's no edges in here whatsoever. So this will not execute at all. We'll just immediately return. And you'll notice that this is now the first element on the stack. I guarantee you can't see that, but it says line 64. It's the first one that has advanced past this line. So we're going to start falling back. Bam, that element fell off the stack. If I advance forward here, there's no more edges in F, so we're going to fall back. Now we're back at H. There's no more edges in H, so we're going to fall back. We're at C, no more edges in C, so we'll fall back. And now you'll notice that we're back to only 2 recursive calls here on the stack. So we are back at B. We're going to go through each edge in B still, so our next edge is going to be the one containing data D. So we are now about to step into this, and we'll do that. And I'm going to start to go a little even faster for the next... Nope, actually this is what I wanted to show. So we add D to our list of visited edges after we print it to the console, and then we're going to go through each edge and edges. The next edge we're about to visit, or going to attempt to visit, is data F. But as we know, we've already visited F, so we're going to check to see if it doesn't contain that, which it does. So you'll notice that it does not execute that recursive call. So I'll go to the next edge. It will be the next node, which I believe is G. Yes, G. We're at this point. We're going to continue on. We're going to visit it. G is printed to the console for each edge. Let's recursively call. We're now going to print J to the console, so we are at this point. Then we're going to step through each edge there. Well, there's none, so we're going to fall back. We're back at G. No more edges. Fall back. We're back at D. No more edges, so we're going to fall back. Now we're back at B, all the way back up the top. So B has one more edge in its list. We will recursively iterate, or recursively. I keep saying recursively iterate. That's the complete, I don't know, oxymoron something. It's not correct. But we're going to recursively call on that. We are now at E. We're going to step through. We're going to visit E, go through each edge, make sure we haven't already visited it. We haven't, so we're going to step in. Now we're at K. So we are at this point. Again, I don't know why the purple's missing there, but now in K, again, we're going to visit it, and then we're going to see that each edge in edges has already been visited. So we're going to fall back, fall back, fall back, back to A, fall back. We're back at depth first, so we're going to fall back to main, and we're done. If I pull the console all the way up, you can see A, B, C, H, F, I, D, G, J, E, K, which is the exact order that we expected to visit these nodes. A, B, C, or B to C, C to H, H to F, F to I, then D, then G, then G, then J, then E, then K, and then we're done. So that is it for depth first. In the next video I will do breadth first, which is a bit different, and I hope to see you next time.